Okay, now we want to talk about adjusted R squared versus R squared. Now the basic problem with R squared, remember, is what R squared does is it takes the variation, the percentage of variation that doesn't fit from the model. So it's taking the yi's minus y hat i's squared divided by yi minus y bar, oops, not yi, just y bar squared, 1 minus that. Okay, so it's looking at, and we'll just go with nice straight line there and a couple of points, 3 points, and so it looks at, it takes that, right, and says, okay, that's not fitting the model. Let's sum up those deviations squared, look at the total variation, get that ratio, and so that's what's not working, is this fraction over on the right. So then if we take 1 minus that, we get what is working. Okay, so that's R squared. Well, the problem is, here are 3 points. Yeah, that's maybe the best straight line I could fit through there. And maybe for some reason I realize it really should be a straight line, that the best idea of the model is a straight line. But if I had those same 3 points and instead decided to fit a quadratic, it would be perfect. Okay, and so this part, these deviations, would be 0. And so in this case, and actually in the last video I don't believe I ever pointed out that R squared, because it's a proportion, is always between 0 and 1. Here we get 0, so R squared for the quadratic, I'll put a little q there, we'll make that R squared linear, is whatever we got there. But this will be 1 minus 0, or 1, it'll be perfect, right? This model fits the data perfectly. And but it may be that we know that's not the right model. And to exaggerate a little bit more, we could add a few more data points. There are 5 data points, and what I know, I'll put this data point down here a little further, make it a little easier for me. But what I know is I could find a 4th degree polynomial, and it might not look quite that nice, but I can find a 4th degree polynomial that will go through every one of those points. And in that case, for that 4th degree polynomial for those 5 points, I will get an R squared of 1. It'll be perfect. Okay, but the problem is that what happens is I've biased my model a lot, right? As I add more data, let's compare these 2 models. So here, I'll try to draw those reasonably close to what I had. Here's the straight line model. As I add more data, say, I get more data as time goes, you see this top model up here did a horrible job of trying to predict the new data, right? It's way off the model, whereas here, as I get some of those new data points, maybe they're in here somewhere, something like that. Wow, this model here, the straight line model, seemed to predict them better, right? I mean, in that Yeah, they're going along a straight line. This is waving all over the place. Okay, and what the problem is in fitting a model, we get this thing called a bias variance trade-off. And again, we can see the bias, right, is more parameters, right, that because here I've got just y equal mx plus b in the straight line model. Up here with this one, I needed a coefficient on the x to the fourth, coefficient on the x cubed, coefficient on the x squared, and then the m and the b for the x and the y-intercept. So more parameters. Okay, what that means is less variance left over from the model. Okay, but more bias in the model. And then if I go with fewer parameters, right, fewer parameters, well, then there's going to be more variance left in and I'm going to call it test data here. This is the data you're working with. We'll call it the test data or the training data. Okay, test or training data. Okay, but there's less bias in the model. So it's always a trade-off. And that's one of the big things in fitting models and so forth is trying to determine, whoa, what just happened? I don't know what just happened. Jungle Wild? I don't know what that was. Looked like a lottery thing. I think it was an ad. But at any rate, so we can always fit our data better by adding more parameters. But as we add parameters, we get this bias that new data probably won't be very close to our predictions from the old data because, if you think of this wiggly model. But on the other hand, if we use fewer parameters, well, it won't look as good going through the training data, but for new data, predictions on new data, it won't be so biased. It won't expect to be turning so much or something like that. That's a nice visual here with that turning, but it's really, you could do it all with linear stuff too. You could just keep adding more and more linear terms, more columns of data, and make them linear. So, but you probably don't want all that. And so what we'll do is, we'll try to balance the trade-off. And if we're using multiple regression anyway, which we'll be our biggest tool. We can use adjusted R squared. And what adjusted R squared does is it takes into account your parameters, your number of parameters or your columns of data, as well as the R squared itself. Okay, so for adjusted R squared, okay, adjusted R squared, what we want to do is we want to take that original part that was not explained by the model, so yi minus y hat I squared over yi minus y bar, oops, no bar there, sorry, squared. We want to take that and multiply that by something that penalizes us for using more columns of data, because a parameter in multiple regression is a column of data. That might be going to x squared and x cubed and so forth, but to make those, you make columns of data. So we want to take something like n minus 1 over n minus k minus 1. Okay, so here n is lines of data, and k is columns. Of data, not including y, so not y. Okay, so this is our columns of data, and notice what happens that since we're subtracting k, as for any given number of lines of data, as k increases, as we increase the number of columns, the denominator gets smaller, and so this multiplier gets bigger, which makes this whole thing bigger. But then, just like in the R squared, we take 1 minus, which would make our adjusted R squared smaller. Okay, so in general, adjusted R squared will always be smaller than the R squared for a given run, but we can use the adjusted R squared to help us balance what we do, what we pick for a model for our data. And I'll do an example of that with some actual data and technology and look at that adjusted R squared. Now, the way actually, gosh, I've run out of room here. I guess I'll have to go to page 2. Not good timing on that, but the way I tend to calculate adjusted R squared is I take 1 minus the R squared. Okay, now what that does is 1 minus the R squared gets you back to this. That's 1 minus R squared, and so I take 1 minus R squared, and stuff's so weird, and I multiply that by the n minus 1 over n minus k minus 1, and then I take 1 minus that whole thing to get the adjusted R squared. So a couple of 1 minuses. 1 minus, and then in parentheses 1 minus the R squared times our fudge factor for number of columns used, and and then subtract that from 1, and we get our adjusted R-squared. And so what you can actually see with working with data and adjusted R-squared is, again, you may, let's say I just have these 4 data points, and I fit a line with that. Well, what I might find is that my R-squared on something like that is equal to, maybe 0.8, 80% of the data are explained. And then the adjusted R-squared is going to be a little bit smaller because, and I could tell you exactly what it is, but I don't wreck a good story with facts. It's going to be a little smaller. Let's say it's 0.7. Now, what can happen though is that, okay, so I go to a quadratic, and same data, and what might happen with the quadratic is, I don't know, maybe it would look like that, and we get an R-squared of maybe 0.85, and then when we do the adjusted R-squared, well, we may see that that's, let's say, 0.75. Well, in that case, unless I have any other reason to doubt it, I might want to go with a quadratic over the linear, because not only did the R-squared increase, which I expected just because I used more columns, but the adjusted R-squared increased. But then what could happen is, so suppose I go to a cubic, and maybe that cubic looks like that, because a cubic could hit all 4 data points. And so here we all of a sudden get an R-squared of 1. Wow, that looks fantastic. But it could turn out that the adjusted R-squared on this is actually something more like 0.7 again. In which case we see by adding that parameter of the x cubed, that column, the x cubed column, we actually lost some ground on the adjusted R-squared, and therefore we probably would want to pick the quadratic. Again, we need more information to really know, but just based on the adjusted R-squareds and so forth, I probably would go with the quadratic in this case because it had the highest adjusted R-squared. And when you go with more columns of data, more parameters and all that, and get these beautiful R-squareds like that one, but maybe the model's really not too great, we call this overfitting. Okay, and what you don't want to do is overfit. Simpler is better. Overfitting usually is trying to make things more complicated than they need to be. And so overfitting is bad. Okay, we don't want to do that. And in this module and in this class, what we'll do is we'll try to take a look at this adjusted R-squared as we look at different models. Okay, so that's the idea of adjusted R-squared, and we're just trying to battle the bias variance trade-off and overfitting, okay, by using it. And that's just, it's a tool to help us understand how our data fitting is going. Okay.